Okay, just a little bit more about data structures. Another type of variable that we could have is a factor. So this is usually used within a function when we have some sort of categorical variable that has a defined number of levels. And these could be ordered levels or unordered levels. It doesn't really matter. But think of these as different types of treatments in an experiment, or different grades for students, or different types of cars. Anything where we have a distinct and discrete set of levels should be thought of as a factor most of the time in R. So here, for example, we could use the rep function on the sequence 1 to 2, 4. So this is going to repeat 1 4 times and 2 4 times, and then we create labels for this. So this ends up standing for treatment 1 and treatment 2. So notice we get treatment 1, 1, 2, 3, 4 times, and treatment 2 also 4 times. So the levels of the factor are treatment 1 and treatment 2, and each appears 4 times. Also, we could do a similar function here. Now we have 3 levels to our treatment, low, medium, high, and we're going to order them because there is a distinct ordering. Here there's not a distinct ordering. Functions you can use on factors, you can tell the number of levels. You can return the number of levels using in levels. You can re-level them. So this is if you need to reorder for some reason. Also, you could reorder this way. You could generate factors by specifying how they have a pattern in their levels. You can also create factors by cutting a variable x into intervals. So you have to define the number of breaks. So sometimes you have some sort of continuous scale variable and you realize you really don't want it to stay continuous scale. You want to break it into intervals. The cut function can be useful for that. There's some more options on the cut function that you might need in the future too. Here's some examples. So here f is going to be a factor for 3 treatments, and there's going to be 2 cases per treatment. So we're using that GL function with a 3 for the number of treatments, a 2 for the number of cases per treatments, and here's our labels. Treatment 1, 2, 3, we're using that paste function from a few slides ago. So this is going to read treatment dot 1, treatment dot 2, and treatment dot 3, because our separator is a period. Okay, so we can get back our number of levels. So what will that give us? Take a moment, go and evaluate and take a look. Also, we can run the in levels function on there and re-level it where level 2 is going to be now the first level. Similarly, we can take a look at this, by the way, and make sure you can understand the difference between these different functions. These two in particular can be a little confusing. So here, x is going to be a vector of uniform 0, 1, 10 uniform 0, 1 random variables. We're going to cut this into 3 breaks. So this will give us 3 intervals here. Or we could cut it at given points. Usually you do have it cut at given points. That usually makes more sense, but you can also have it cut so it's equivalent. Finally, dates and times in R. R has objects that are dates and objects that are dates and times. So we can do both. If you need to look up for particular types of formats that you can use, just look at date time classes in the help file, and that will get you I think what you need. We're going to just take a look at dates because this can become a little overwhelming if we don't limit ourselves. So our date object is going to have this general format: year, month, and then date. The operation with dates are really pretty easy to deal with. You can do subtraction or addition on dates, and it'll calculate the number of days between those dates. You can compare using logical operators. Okay, there's also this set of functions that will apply to dates that could be useful as well. Sometimes we have strings, character strings, that we need to actually convert over to that date format. Remember, we did the same kind of stuff in SAS. Any character string any character in the format string other than the percentage symbol is going to be interpreted literally, okay? This percentage symbol is a special formatting in R that will allow us to do these kinds of character string to date conversions, okay? So some common conversion specifications that we can use within R include the following. I'm not going to go through this whole list again. We use them when we need them, but let's just go and look at one application. So we could do %D, which will give us the day of the month, okay? So let's see how that's applied. Here we have a character string vector. Notice these are not entered as dates, but would just be read as character strings within R. R would have no way of knowing that dates.1 is actually dates. So now we're going to run it through the function as.date, and we're going to tell R that this is the format. So notice %D is the day of the month. So right there, that gives us that information that first the day of the month is read. Then %B is the abbreviated month name. So that again is telling us that's the next part of that character string. And finally, %Y is the year with the century. Okay, and that's what we've got in the last part of the character string. So once we run it through that as.date function with that formatting applied, we actually get date formatted elements from that vector. Here's another example. Notice because the character string has these dashes between them, we have to include those dashes in our format, or else again, it will not know, the R engine will not know how to interpret those dashes. So this is, I think, really nice and flexible and will accommodate just about anything. A little bit easier to use, perhaps, I think, than the SAS date conversion. Finally, to create a sequence of dates, I'll let you read through this a little bit on your own. There's maybe too much material here, but notice you really just have a beginning and an end and then a by. And it tells you how many, how to increment, where to start, where to end. It's a pretty nice way to generate a date variable. We can cut dates. Okay, so this is similar to the cut function we just looked at. So X is going to be a vector of dates, and we can cut it according to a number of breaks or a specified place to break. We can also do operations with dates. Okay, so we can subtract, we can add, we can compare. So, for example, is January 8th bigger than January 1st? Why, yes. We can do January 8th minus January 1st, and it'll tell us the difference is 7 days. We can do January 1st minus 14, and that will tell us what the date is 2 weeks subtracted from January 1st. Let me make sure that's right. Yeah, January 1st of 2011 here. Then we could add 7 days to January 1st. So we have all of these ways we can use that date. We can also extract parts. So if we just need the year, if we just need the month or whatever, we can extract that out of a date object as well. Last topic, missing data. In general, missing data should be denoted by a capital NA, not available. How a function handles missing data actually depends on whoever wrote that function and what they decided to do. A common argument is na.rm equal true, which means it will ignore if you include that in a function call, but not every function call will let you do that. Okay, so for example, if we have a vector x, and notice the last element is missing, and we try to run the main function on there, it will give us back an NA because of that missing value in the vector. If I put in na.remove equal true, it will ignore that and not include it in its calculation. If I run a function like which though, which x is bigger than 4, it just automatically ignores that missing value. So every function is a little different. So if it's a function I'm not very familiar with, I actually look up the documentation to see how it handles missing data or test it out myself with a little trial. Quantities that aren't a number, such as dividing by any number by a 0, will give you not a number response. And our NaN is another way that we sometimes see missingness, okay? It's not equivalent, but it gets kind of treated that way by certain functions, okay? Undefined or null objects can also be denoted by the null expression. This is useful when you have objects from function calls in particular, okay? So if you want to, say, add row labels to a matrix, but one of them you do not want to add a row label to, you could use the null expression. Finally, detecting missing data. Is.NA will detect the missing data for a vector or a matrix or array. Is.NaN will test for is not numeric, and is.null will just test for whether or not it is null. All right, so we can use this in various ways. Keep in mind, however, that we need to be careful about what type of object it operates on. For example, is.NA operating on a vector will give us back a logical vector. That may not be what we want. We may just want a single value telling us that there is a missingness in that vector, which means we need to run is.NA through the any function. Okay, so just keep that in mind. It does preserve the structure of whatever object that you are passing through that function.